Hi. As a part of our lecture series, today I will be discussing a basic introduction to systems on chip, or more commonly known as SOC. A lot of y'all must have heard this term for the first time, but don't worry. By the end of this lecture, I'm sure that all of y'all will understand what we mean by SOC. So, as a part of today's lecture, I will be discussing first, what is an embedded system? What do typical embedded systems look like? How do we program in embedded systems? Again, these are conceptual points that I will be discussing. Then I will explain the introduction to SOC, or systems on chip, and we will look at the advantages and then the understanding of programming using standard SOCs. The aim of this lecture is to transition your understanding from traditional embedded systems towards SOC. So this lecture will be purely conceptual. As you will move further in the course, you will see at different practical SOCs which will make things clearer for you. Okay? So what is an embedded system? The most basic definition of an embedded system is that when I take some software or a program, so if I have some program with lines of code and I put it onto some applicable hardware, which would be a microcontroller, microprocessor. The reason why I use the word applicable is because not all software fits on all hardware. You have to see the compatibility. So if I take some software and I put it onto applicable hardware to perform a particular application or task, then what I get is an embedded system. The term embedded system is from the English word embed, which is to fit something or to put something inside another object. Okay, to embed. Alright, so that definition taken, let's understand what do typical embedded systems look like today. So if I take a traditional embedded system, then the first most important thing in an embedded system is the controlling element, which is your microcontroller or microprocessor. This term means mu. Mu means micro. Okay, it's the symbol for micro. So I would have the microcontroller or the microprocessor in the center, which is my controlling element. And then I would have some input devices. I would have some output devices. So input devices would be switches, buttons. Then I would have a keyboard. Then in today's world we have the touch screen as well. So different examples of input devices. For output I would have LEDs, LCDs, printers, speakers, and so on. But it's not just that. In an embedded system you also have power, because without power there is no functioning. Then you also have the concept of clock, because all the digital devices, they work on clock. If you know that this is clock. Then after that, if you can guess, there is another very important component, which is memory, because you have to store data and the program in the memory. Some microcontrollers or microprocessors also have memory inside the chip. Okay. Then we have another category, which is a very important category. They are called as interface ICs. ICs stands for integrated circuits. So in interface ICs, you would have your ADCs, which is your analog to digital converter. You would have your DACs, which is digital to analog converter. Then you would have your UART, that is for serial transmission. So then you would have your USB chip, something that, so for example, you want to do a USB interface, so you would have a USB chip with the outside world. Then there are different SPI, I2C, and all of these. So a typical embedded system has all these components that you have. In today's world, there are a few more categories. One of them is power distribution, because nowadays distributing power across the chip or across the board or across the system is important. And another category is clock distribution, because a lot of the interface ICs and the microcontroller, they work on different clocks. So this might be one clock, then another chip might work on a faster clock. So you need proper clock distribution as well. So this being your typical embedded system, it's very important to understand that this is just an example of how a typical embedded system would look. You can add or subtract categories or components, but typically you would have all these components. So that said, let's understand how do we program using embedded systems. So the most basic style of programming is something called as Hex Programming or assembly language programming. So what we would typically do is we would write a hex program or an assembly language program, then convert it into binary, which is again hex itself. So your assembly converts to hex. Hex is basically binary, and then I put this program either onto the memory on the chip of the microcontroller or the memory of the system. Okay. So that was the most basic style. In today's embedded systems, the applications are very big, as in the complexity is high. So if we draw a very simple curve of complexity versus number of assembly instructions, the curve actually grows exponentially. This is again typical. You can come up with a different example, but what I'm trying to say is the more complex your program is, the number of instructions increases. Hence, programming using hex is very difficult for complex programs. So what we do in today's world is we write the application in a higher level language, for example, you have C or C++, and then what we do is we put this C or C++ program through something called as a compiler, and this compiler converts this to assembly language, and then we do the same process again. So because the applications with a high level of complexity, we write in a higher level language which then goes through the compiler. And so for example, if I want to write a program which interfaces with a ADC or an analog to digital converter, then I would write that in C++, and then my microcontroller will receive the program in binary, and then my microcontroller can start talking to my ADC. And then you can receive analog signals which will then get converted into digital. Okay? I hope this basic understanding of how we program in embedded systems is clear. So before I move on to the next topic, I want to discuss a quick point that VLSI in the field stands for very large scale integration. So effectively, there was a person called as Gordon Moore, and he predicted that if I have a chip or an IC or an integrated circuit, the number of transistors, now by transistors we would have FETs, BJTs, MOSFETs. I'm sure you've heard all these terms. So the number of transistors on a chip, so if I draw the y-axis, number of transistors would double. So the number of transistors would double every 18 months. So this would be 3 years, 1.5. So 18 months is equal to 1.5 years. So if I make this time in years, so every 3 months, if this is x, this would be 2x, 4.5, this would be 4x, and so on. So in short, what I'm trying to say is, as time progressed, we as engineers could fit more and more hardware. By hardware I mean FETs, BJTs, and MOSFETs on the same chip. The reason is because the transistors, for example the FETs, got smaller and smaller with time. So then somebody really smart asked a question, is that given an embedded system like this, can I take some of the components, given an embedded system like this, can I take some of the components and fit them onto the same chip? So that's the question. That given these components, let's write the question down. Can I fit some of these components on the same chip? The answer is yes. So let's see. Can I put switches and microcontroller on the same chip? No. Please understand, it's the same chip. Can I put output and the components on the same chip? No. So the answer is, all that is made out of silicon basically can be put on the same chip, namely the interface ICs, the microcontroller, the power distribution, the clock distribution, the memory. All of this can be put on the same chip. So that is what we call as SOC, or systems on chip. In definition, if I can take certain components of my embedded systems and put them on a single chip, then I can call it a SOC, or a systems on chip. It is also pronounced as SOC or SOC. So I hope that it's clear that if I can take certain components of my embedded systems and if I put them on the single chip, then I would get an SOC. So the advantage of using an SOC is, since a lot of my things actually came onto the same chip, like my microcontroller and my interface ICs and my memory, so the distance reduced, hence my speed increased, and also the delay of taking a signal outside a chip is far greater than sending a signal on a chip, on the same chip. So previously the memory was outside, so the microcontroller would have to send the signal outside the chip, but now it's sending it on chip. Hence, since the delay is much better, hence the speed is lesser, so hence here doing it on chip is faster. Okay. Second, obviously, since everything is coming inside, my size reduces, hence my cost reduces, and also since everything is on chip, my power of the system also reduces. So these are a few advantages of using an SOC. That said, let's understand how do we program using an SOC. So considering that this is my SOC, my programming is still the same, where I am still programming the microcontroller. Here also I would write my program in a higher level language like C or C++. There are other languages as well, and then I would convert it to your hex code, and then I would program it here. Not a big change. However, in today's commercial SOCs, like a PSoC or Programmable PSoC by Cypress Semiconductors, or the ARM mbed platform, which involves the ARM microcontroller based SOCs, the programming is a mixture of C and C++ and also something called as APIs, and I will just discuss that right now. What do we mean by APIs? But before that, I would like you all to understand that programming using an SOC is the same typically, is that you are writing a higher level program and then you are putting the hex code either in the memory of the microcontroller or the memory of the SOC. Okay. So let's understand the concept of APIs. API stands for Application Programming Interface. So let's understand this. I will take an example of a microcontroller with a ADC. ADC stands for Analog to Digital Converter. Now, traditional ADCs have a few signals. They have the SOC terminal, they have the EOC terminal. Now, this SOC means not system on chip, but it means start of conversion, and EOC stands for end of conversion. Okay. So if as a microcontroller I would want to interface with an ADC, the input for the ADC would be an analog signal and the output would be a data, let's say 8 bits. So my job is to sample an analog value, and then convert it to a digital data which my microcontroller can then read. For that, first my microcontroller gives a signal to my ADC which says SOC is high. My ADC will then start the conversion and then will say, okay, I am done with the value, please take this value. So there is a step, which is step 1 is SOC high, then wait for EOC. So S1, step 1, step 2, step 3, wait for EOC. Once EOC is high, then I will say, let's take data. Now, if you see, this process takes a few steps. So every time that I want to write a program that wants to read data from the ADC, I have to write a higher level code in C or C++ which has to do this. Do you agree? So in industry, they want designs to be made faster. Hence, programs are they try to make it smaller. Okay. So what they've done is, in my program, instead of having a SOC equal to 1, then wait on EOC, and then reading the data, all of this you just convert it into one function called as, for example, ADC underscore read. So this function would in effect do all of this. So in the future, in my program, if I would like to read an 8-bit value from my ADC, then all I have to do is I write in my program ADC underscore read, and I give this value to a variable X. That's it. The style of programming using these functions is called as the API style of programming, is where you take given APIs. So it is an application programming interface where an interface is given to you like this for programming a particular application, which in our case was reading from an ADC. Okay. So similarly, if I want to, let's say, put a value on an LCD, you have an LCD screen and I would like to write or display the value on an LCD, you would have a API for an LCD which would say LCD underscore write. That's all. So LCD underscore write hello, and then all you would have is on the LCD you would have the term hello. So using APIs makes the program smaller and simpler to understand. Okay. Now, most commercial SOCs, like as I mentioned, most commercial SOCs like the PSoC or the Programmable System on Chip from Cypress or the ARM mbed platform It's mbed, M with BED. And most of them have an API style of programming, and I'm sure as a part of the future lab or course you will be learning one of these platforms, and you will see that all of them have APIs to work with LCD, ADC, UART, USB. So in effect, you can write smaller programs and simpler to understand and build more complex applications. Okay. So I hope that this understanding of API is clear. So let's just quickly recap today's lecture. In today's lecture, we understood what is an embedded system, the concept of having a particular software and we put it onto an applicable hardware for an application. Then we saw that a typical embedded system has a microcontroller, input-output devices with some interface ICs, with power and clock, with power distribution and clock distribution, with memory. We then saw how do we program using an embedded system. We write in assembly language or hex and then put that onto the memory. But then as we write larger programs, the complexity increases and hence the number of instructions increases. So we prefer using a higher level language like C, C++. In today's world, we also call it as embedded C. And then we put it through a compiler that then converts it to hex, and then we go through the same process. And then we understood that as we can fit more and more transistors on the same chip, we try and put some of these components of the embedded system onto a single chip, and that is what we call as SOC, or systems on chip. And then we saw that the advantages are speed, size and power, because as my distance between the components reduced, the speed increased, and also taking a signal on chip is faster than taking it off chip. We also saw that the size and the power is lesser. Then in SOCs we saw that the basic programming is still the same, that we write a higher level language and then convert it to hex and put it through into the microcontroller. Then I explained the concept of APIs, or application programming interface, and we saw that for a particular application you have to go through certain level of steps. If you have a higher level API, then we can actually make the program smaller and simpler and effectively build more complex applications. So I hope this the basic intro to SOCs was clear. As a part of a future lecture, we will now see a particular SOC platform which you will then continue the course on. Thank you.